Hello everyone, myself Bhumika. Currently I am pursuing BTech in the stream of Computer Science and Engineering in Srinivasa Ramanujan Institute of Technology. Today I am going to explain you about multiple processor scheduling. Introduction to multiple processor scheduling. When multiple processors are available, then the scheduling gets more complicated because now there is more than one CPU which must be kept busy and in effective use at all times. Load sharing revolves around balancing the load between multiple processors. Multiple processor systems may be heterogeneous, different kinds of CPUs, or homogeneous, all the same kind of CPU. Even in the later case, there may be special scheduling constraints such as devices which are connected via a private bus to only one CPU. This book will restrict its discussion to homogeneous. Next, approaches to multiple processor scheduling. One approach to multiprocessor scheduling is asymmetric multiprocessing, in which one processor is the master controlling all activities and running all kernel code, while the other runs only user code. This approach is relatively simple as there is no need to share critical system data. Another approach is symmetric multiprocessing SMP, where each processor schedules its own jobs either from a common ready queue or from separate ready queues for each processor. Virtually all modern OSs support SMP, including XP, Win2, Solaris, Linux, and Mac OS. Next, processor affinity. Processors contain cache memory which speeds up repeated accesses to the same memory locations. If a process were to switch from one processor to another, each time it got a time slice. The data in in the cache for that process would have to be invalidated and reloaded from the main memory, thereby obviating the benefit of the cache. Therefore, SMP systems attempt to keep processes on the same processor via processor affinity. Soft affinity occurs when the system attempts to keep processes on the same processor but makes no guarantees. Linux and some other OSs support hard affinity. The process specifies that it is not be moved between processors. Next, main memory architecture can also affect process affinity if particular CPUs have faster access to memory on the same chip or board than to other memory loaded elsewhere. Non-uniform memory access (NUMA). As shown below, if a process has an affinity for a particular CPU, then it should preferentially be assigned memory storage in local fast access areas. Below is the diagram for non-uniform memory access and CPU scheduling. Next, load balancing. Obviously, an important goal in multiprocessor system is to balance the load between processors so that one processor won't be sitting idle while another is overloaded. Next, systems using a common ready queue are naturally self-balancing and do not need any special handling. Most systems, however, maintain separate ready queues for each processor. Next, balancing can be achieved through either push migration or pull migration. Push migration. Push migration involves a separate process that runs periodically, example, every 200 milliseconds and moves processes from heavily loaded processors onto less loaded ones. Next, pull migration. Pull migration involves idle processors taking processes in ready queues of other processors. Push and pull migrations are not mutually exclusive. Next, note that moving processes from processor to processor to achieve load balancing works against the principle of processor affinity. And if not carefully managed, the savings gained by balancing the system can be lost in rebuilding caches. One option is to only allow migration when imbalance surpasses a given threshold. Next, importance of multiple processor scheduling. Improves system performance. Multiple processors can execute different processes simultaneously, which increases overall speed and efficiency. Next, better resource utilization. Work is distributed among processors, so no CPU remains, others are overloaded. Next, reduced response time. Tasks complete faster because they are processed in parallel, improving system responsiveness. Supports multitasking and parallel processing. Many applications like scientific computing, video processing, and databases require parallel execution for better results. Higher reliability and fault tolerance. If one processor fails, others can continue executing tasks, making the system more dependable. Next, improves throughput. More tasks can be completed in less time, increasing overall productivity of the system. Next, handles large and complex workloads. Multiprocessor systems are suitable for heavy computations and large scale applications. Next, real world applications. Cloud computing platforms, high performance computing, data center optimization, and gaming systems. Cloud computing platforms. Major cloud providers like AWS and Azure utilize multi-processor scheduling to efficiently manage resources, ensuring optimal performance and scalability for millions of users. High performance computing. Supercomputers leverage advanced scheduling algorithms to maximize processing power, enabling complex simulations and data analysis, significantly reducing computation time. Data center optimization. Data centers implement multiprocessor scheduling to enhance resource allocation, achieving up to 30% more efficiency in energy consumption and workload management. Next, gaming systems. Modern gaming consoles utilize parallel processing capabilities and allowing for smoother graphics and faster load times, enhancing the overall user experience in gaming. Thank you. I hope this presentation has provided valuable insights into multiple processor scheduling. Thank you for your attention.